to a session on fusion and the fusion economy, part 1. Over the next 2 sessions, hopefully, we will be able to get a pretty good sense of why fusion is necessary, why it's much more than what most people are referring to when they talk about fusion, and how we can demonstrate a basic principle of economics. So I want to start from a continuation of last week. Now, we've now discussed in some detail this idea of really being able to think globally, to be able to not just think globally, but be able to have the precision and power to control effects on a global scale and even beyond, as we've seen with what we saw before, which is that with what Ben Dennison presented, which is that global phenomena are caused globally, extraterrestrially. Now, one of the funny things is that, okay, so all the activity that is on Earth, the weather cycles, the tides, the motion, life, and so on, is in a large part powered by 2 major sources, and there are other sources which we will discuss at some point, but 2 major sources of power. One is the sun, and the other one is the Earth itself. So the Earth itself puts out some amount of heat constantly. It decays. There's all sorts of theories on what type of magma or dynamo activity is happening. Either way, we do know that there is a constant source of heat and probably more energy coming from the Earth. And it's not a lot, you can't feel it, but it is cumulatively a lot. So it's about the amount that would power 470 million light bulbs at any one time. And that may sound like a lot, but the sun gives the Earth, so just the surface of the circle that subtends the Earth, the sun's rays, the sun gives the Earth 3,700 times more than that. So just to give you a sense of most of the activity that is being powered right now on Earth is coming from the sun. Now, so you think, if we wanted to control the weather on a global scale, it actually becomes a process of understanding our sun. It becomes a question of understanding our own powerhouse. And this is really funny because to reflect back on, because we didn't actually know very much about the sun until the past 100 years. Before the past 100 years, before 1900, really 1901, the sun is just hot. It's a furnace. And as far as we know, the only thing that was, besides heat and light, that we knew about it was that there were these spots that you could see, you could count. They at least, I think, far back as about 300, a little past that BC, Chinese and people in Greece were counting sunspots, or at least observing them, not maybe counting them continuously. They were definitely counting them almost continuously in the 1700s, because they were able to note that the sun had dropped off, giving out or showing sunspots for a good 50 years, from 1645 to 1717, so more. and that was known as the Maunder minimum. And you'll see accounts of this in various works. But so from that, at least, we knew, so this is, by this early 1700s, we knew there was some kind of cycle. They could see where the sunspots generally occurred, what latitude they occurred at on the sun, and so on, but that's sort of all we knew up until the early 1900s. Now, what did we find out in the early 1900s? Well, first of all, there were two things we were studying. One, nuclear power, or nuclear transformations, and then two, cosmic rays. And these are two incredibly powerful, or these are two sources of incredible energy that we had never encountered before. And really, prior to the current period, even up to about 50 years ago, cosmic rays were just anomalously high energies that we could not replicate. And that was our source of a lot of our forefront research. But up until then, we were really we were still hypothesizing, and people had thought, okay, well, what powers the sun? Okay, we're going to figure out what the sun is. I mean, there's got to be something powering it, because it is obviously giving us at least heat, at least light, at least. So, what is it made out of? If you were to, and this is a fun exercise, if you were to take the volume or the mass of the sun and take that same amount of mass of petroleum and burn that, how long would you have? How many years would you have of the sun left? Now, it turns out if the sun were made of petroleum, you would get about 7.3 thousand years. Now, that's actually not very much. And if you look at the archaeological records, we have much, much longer of records of life, even, than that. So it was really when we started to get into nuclear processes, we were starting to understand fusion, that we started understanding anything about the sun. And now we know there's more than just light sunspots. There's magnetic activity, there's particles, there's charged discharges, and so on. There's a lot of activity happening. The energy we're getting from the sun, the influence we have from the sun is much, much more. Now, that's not to say that we already know what the sun is all about. We still can't forecast what it does. And, yes, you could say that now we understand fusion, now we understand something about what the sun does. It's more, the way that it's worked is much more like the sun is what we know up to this point. And the next step, whatever we find out next, maybe including into the domains of antimatter and whatever the next step is probably what we're going to define, or will open a domain into understanding, again, what the sun is. So, there's a huge so there's the aspect of understanding globally what's happening on Earth. Then there's also the aspect of understanding where our role is, what our role is in the universe, and taking into account the fact that we can continually come to understand what controls the solar system and control it. And that's really going to be the key, is really have this idea that we will create, and we have to some extent created, a sun on Earth, many suns on Earth. And I mean, just stop and think about what that means. Maybe the practical thing is, yes, the sun is going to, our current sun is eventually going to become very uncomfortable for us, and we will have to leave it. And so possibly carrying our own sun would be the most practical route to go. I don't know, but it's just a fun sort of thought object. What I want to do is I want to back up and go through some basics of fusion, so we know what we're talking about, and then get on to and end up with some implications for now, for the economy now. So I'm going to pose a disclaimer. What I would have liked to do is to start from a historical standpoint, from Ampere onto Moon. That will have to be held, because I would have to do a lot more work to give it the due credit that it would really require. And I think that's something we should definitely take on in following courses. What I'm going to give you now is some of what the current scientific community knows, or at least thinks it knows, and some more. And we'll see, and we'll judge from there. There's already some very cool, interesting things that that we'll be able to glean from current research, and then also what some of the potential is. Okay, so let's start with this. Let's see here. Okay, so let's start with plasmas. Most fusion, and we're starting with this because most fusion occurs in plasmas. And well, anyway, we'll go through plasmas and then it'll become more obvious. So the idea of a plasma is actually not that difficult. Plasmas themselves are very common. People call it the fourth state of matter. So you've got solids, liquids, gases, and plasmas. Really loosely defined, it's basically ionized or charged gas. So that means that particles that are either positively or negatively charged. We're most familiar with neon lights, things that have plasmas, which we use their properties for, like neon lights. Fluorescent light bulbs have plasma in them. The ionosphere is largely plasma, and then lightning also creates plasmas. And then here's a common one that we are familiar with, but maybe not so familiar with as a plasma. Okay, so what we're looking at here is two plates, negatively and positively charged, which are of very high voltage apart. And what we're looking at is a candle and a candle flame. And if you're familiar with flames, usually they point up, right? There's a sharp point at the tip at the top. Well, this one's not doing that. This one is splitting. There's two tips. One pointing one direction and the other one pointing the other. So what you're dealing with here is, well, here, let's look at the next one. Okay, so what is this? This is actually electricity traveling from one plate through the gas that's near the flame, through the flame, and then back out again. So there's a constant current flowing through the flame. And then this is just a similar case. So part of the smoke is being attracted one direction, the other part of the smoke is being attracted the other direction. So just to give you a sense, this is a flame, which we're pretty familiar with, and it is made of charged particles, or charged gas, or a form of plasma. And we'll start to see that the plasmas, they can be categorized into a very wide range. This is considered a pretty low temperature plasma. Okay, so typically, here's the typical explanation of it, and of fusion, which requires the use of plasmas. So typically they say, okay, atoms are made mostly of a central part, the nucleus, which is positively charged. And because all nuclei are positively charged, if you want to get them to fuse together, that's going to be very difficult because the positive charges are going to try to repel each other. And therefore, in order to get them to fuse, you have to smash them up against each other really hard. And there are variations of that, but that's basically the explanation. So one way to smash them together really hard is to heat up a gas of, say, hydrogen atoms until it's 100 million degrees, which is really hot, and get them to move so fast that they actually smash into each other. Now, it doesn't become that. It turns out to be much more difficult than that. But so, therefore, we found very ingenious ways to heat up gases to incredible temperatures. 100 million degrees is hotter than our sun, hotter than most things we know, astronomically. Okay, so let's start with something. Let's start with this. Okay, so many very unexpected things happened, which was really good. It was very I think it's indicative of a new field of science. So what happened was they tried to heat up these plasmas. They try to heat up all these atoms up to really hot. Let's try to get them to smash together. And what happens? Well, nothing they thought was going to happen happened. Many other things happened which were not at all expected, could not be explained, and really a lot of it still can't be explained. Now, just to give you an example of the complexity, so usually things like if you just deal with ping pong balls or pool balls bouncing off against each other, only the ones that are touching each other, that actually touch each other, affect each other. Now that's not the case with plasmas. So you've heated up a gas enough so that the negative parts and the nuclei have dissociated, have separated from each other. Now, they still affect each other. negative and the positive parts still affect each other. They affect each other. Yeah, so they still affect each other. And then another catch, which is when charged anything moves, they create a magnetic field, which also affects each other and everyone else. So that's already getting kind of complicated for two parts of the same atom, right? That's already two parts. Now it becomes very complicated when you're dealing with a whole gas. And what happens is something very phenomenal. It's very incredible, which is that as each one, you just imagine this, and it does become, it actually, this becomes such a hard problem because in the usual way of thinking, which is something influencing another one, and then that one influencing this one, you will create an infinite body problem. Now imagine this one. So this one is negatively charged. It influences everything else. So not just this one, but all other things in the gas. Everything negative and everything positive. As it influences this one moves and creates a magnetic field, which changes this one and all the other things. Then, as that one moves because of the magnetic field, it creates its own magnetic field, and its influence electrically also changes. So what's happened then is this was the oncoming and sort of pioneering, what do you call it, inspiration for supercomputers, as far as I know. So they have these supercomputers calculate these incredibly difficult relationships. Now what's even more interesting is that these very difficult relationships change. Their relationships change. And what I want to do is assign maybe, well, in the next week, or maybe I'll just add it to the description, I'd like to put together a short reading list. And so, we'll go through some basics here. We'll put together a short reading list on fusion, and Cody will go through some more next week to clean up all the ends, and so on. One of the things I'm going to read, I'm just going to read the introduction, or the first paragraph, to a paper called Elementary Plasma Physics from an Advanced Standpoint. And this is a very fun article. It's in Fusion magazine, and I can put the link for that. So I don't remember when this was written. I seem to think it was written right around when I was born. But anyway, I think it was written in the 80s. Says, in the next several years, the development of nuclear fusion energy will create an astounding conjecture. Within inches of each other will be states of matter that never existed in the universe before. On the inside of a fusion reactor, the heavy hydrogen fuel will be maintained at temperatures hotter than any star known. Several inches from this hydrogen fuel, a magnetic coil cooled to a few degrees above absolute zero will be conducting electricity without measurable resistance. And at a temperature almost exactly in between those of the superconducting magnet and the fusion fuel, man will be watching the whole process of his creation. So hopefully that whets your appetite a little bit to read this article. What the article does go through in broad strokes is a phenomenon which, he poses the paradox right away, is that plasmas are something which we should be able to know, It's using just mechanics, electrodynamics, very common courses in college these days. And yet, they are unexplainable in full. And so that is really one of the major paradoxes, is that technically all the forces and all the different causes are known, and yet what we predict is not what actually happens in physical reality. And you ask any plasma scientist today or fusion scientist, and that's just the common thing. Oh yeah, we don't know what a plasma is. We don't know what it does. To some extent they have, obviously you continue to progress, but it's still completely, no one is going to claim that we know what it is. So that's going to become a very important part of understanding where fusion lies. Okay, so onto fusion itself. So fusion, first of all, it's a nuclear process, meaning it's not a chemical one. The two sides of the equation don't balance out. You put hydrogen and hydrogen in, and you get helium or another hydrogen. But you don't, for those of you who took chemistry, you don't, what goes in is not what comes out. So that's important. You know, I described this hot plasma. It's really hot. All of the electrons have sort of flown away from the nucleus, and if there's no electrons, you can't draw those little electrons that you might have done in school. There's no balancing out of the electrons. Chemistry really starts to have no real meaning once you get into these domains, into these type of temperatures. And so that's one thing to really try to grasp, is that this is not coherent, or maybe it's just in a totally different domain than what we normally know as chemical reactions, chemical changes. Now they do interact, which we'll find, I won't cover here. They especially interact in cold fusion, but they interact in a way to tell us that we know less about chemistry than we think we do. Now, okay, so let me show you, okay, what is this? So one very cool property of atoms is that they're difficult to explain. Their properties are difficult to explain, and that you can't explain them by addition. Now what I mean is that, okay, so hydrogen, you look at your periodic table, or if you look at just how many so-called particles are supposed to be in different nuclei, you would think, okay, hydrogen has one so-called particle, helium has 4, 2 protons and 2 neutrons in it for helium-4. So you would think that helium weighs 4 times more than hydrogen, just a proton. That's not the case. And as far as I know, the way that these vary is all experimental. As far as I know, the graph that I'm showing you, which I'll go through what that is experimental. In other words, that there was no forecast that led to this graph, and I don't know if it's explained yet. So the way that people have tried to account for the fact that the addition of things in the nucleus doesn't work is with this. This is one way, which is with this, what they call the packing effect, which is basically how the parts of the nucleus mass, or the mass of these parts of nucleus, must change in order to account for the fact that things don't add up. So let's see what we're looking at in this chart. In this chart at the very top is hydrogen. It's the most common one, H1. So that's a one particle hydrogen, which is a proton. At the top there, and now the one below that, D2, is actually also hydrogen, but it has two particles, neutrons and one neutron and a proton. Now, the reason it's lower, though, is because supposedly the two don't add up. If you added a neutron and a proton, you actually still get less weight than if you had them separately, and so on. So you seem to be losing mass as you go down this Y scale. Now, if you go to the far right side, uranium 235, it's a similar case. We could go through this in more detail if you'd like in the question and answer period. I just wanted to point out that the difference in these masses, the supposed difference in these masses, is what we end up taking advantage of for nuclear power. So where does this mass go? Well, it was forecasted by Lisa Meitner, according to Einstein's discovery, that the mass turns into energy. Which means that according to this chart, there's two ways we can get energy out of this. One, of this whole process. One is by converting heavy things like uranium into lighter ones, like, for example, chromium or xenon, somewhere in the middle here, which, for those who want to look at fission products are basically in this whole range, from chromium down to argon. It's a huge range of material that is eventually in fission ash, basically, used fission fuel. Now, the other way we can get energy is from the left side. I hope the left and right are the same for you. Which, as you see from the drop, so in this case, for example, we'll go through the different reactions in a second, but let's say we convert hydrogen to helium. Now, where's helium? Helium's all the way down there. That's a huge drop. And so that's what we're planning to do. That's what theoretically is being taken advantage of. Okay, now I'm going to go through this chart. Right now it's a bunch of letters and numbers, but I think it's useful to go through. These are the most possible or potential fusion reactions. So D, like I said before, is a form of hydrogen. It's a heavier hydrogen. It's called heavy hydrogen. It has a neutron in it. A neutron and a proton. T is also hydrogen. It's called tritium, and it has a proton and two neutrons, so it technically weighs 3, so therefore tritium 3-1. Now, so the first reaction here, deuterium and tritium, creating helium, so a regular form of helium, and a neutron, is the most, this is the type of fusion right now that most reactors are going for, this deuterium and tritium reaction. And so you see, okay, so these MeV terms on the side, next to helium is 3.5 MeV, and next to the neutron is 14.1. MeV stands for mega electron volts. Those represent energies. So generally that means the speed at which that is corresponding to the speed at which the particle comes out and so on. Okay, so next one is deuterium and deuterium. So you can just have two hydrogens of the same kind, heavy hydrogen, you create tritium, which is also another hydrogen and a proton. That same fuel, you're putting two heavy hydrogens into the same reactor, will half the time produce the first one that we were just talking about, and the other half of the time will produce helium-3 and neutrons. Then the next one is, again, hydrogen, deuterium, and helium-3. Now we've now heard some amount about helium-3. It can be found on the moon. It's made from the sun is exporting it out at all times, and can be used for fusion fuel. So deuterium and helium, tritium and tritium also produces helium. And then here's the two other helium-3 reactions. So the first one was helium-3 with hydrogen. Here's another one, which is helium-3 and helium-3. The next one is helium-3 with a heavier hydrogen than the one before. And that's just to give you a sense. There's 10 on here, so there are many possibilities for fusion fuel. They vary in their accessibility, and they also vary in their products. And so I want to take a look at the right side here of the equation. So the ends are neutrons, and the interesting thing about neutrons is that they're not charged. So everything else here is charged because you're dealing with just the nuclei. You're dealing with such hot temperatures, you're just dealing with the nuclei. That means that you're just dealing with the nucleus, meaning that it's positively charged. So let's look at the first one. Number 1 has helium and a neutron. Number 2, 1 has hydrogen and a proton, and so on, right? So the ones that have neutrons that come out are called neutronic. And the ones that don't have neutrons come out are called aneutronic. Pretty simple, right? These have various uses for us. In general, for example, propulsion, we would like things that are aneutronic. And so if you look at the different reactions where that occurs, one of them is helium-3 and helium-3. Number 5. Another one is number 3, deuterium and helium-3. The one above, number 2i, that only happens 50% of the time. So again, that's aneutronic, tritium and protons come out, but it's only 50% of the time. So you can't guarantee that no neutrons come out. Now the pesky thing about neutrons is that because they're not charged, they can't be controlled by magnetic fields. They can be used for many, many other things, though. And so, in some sense, when we're dealing with fusion, when we're dealing with something more than just energy, and we're actually dealing with transforming matter, then we will have to be more precise about what we want out of this whole thing. The last one, I'll just point out one more, which is the last one, the proton, and the P is for just a proton, which is basically hydrogen, and B is boron, proton and boron, which creates 3 helium atoms. And this is what is being pursued right now by a few different people in the fusion community. But basically the first one, the second one, and the last one as far as I know, are the only ones right now being pursued in the fusion community for fusion. Do you know anything else?
Well, the helium-3 in terms of the electrostatic.
Right, and yeah, right. There's some research which is moving along more slowly than preferred into helium-3 deuterium, I think. So this is number 3. So I just want to go through this because to get you a sense of what types of things we're dealing with. Oh, one more thing is, as far as the light atoms. Well, I don't think I need to get into that. Deuterium. One more thing is deuterium is we get it from water. There's some portion of just regular water is heavy. It's so-called has an extra neutron, and then tritium is not very common in nature. We generally get them from bombs or we breed it. I think we have, yeah, we got them from Soviet Union bombs, basically. Okay. It's just a few more quick, I guess you consider basics. Okay, so when you put actually, I don't think I can go through this. Okay, so just a few more things, and then I'm gonna get to how we produce fusion now and its effect on the economy. Okay, so what is this? This is basically how any magnetic fusion works. This is just the first step. So, like I said, when you're dealing with charged things, you have magnetic fields and electric fields. Turns out that if you put a magnetic field that's pointing in one direction and you introduce any charged particle that's not exactly parallel to that direction, it tends to spiral around it. It tends to spiral around the field that you made. And this is one of sort of the first order of how confinement occurs in a nuclear reactor. So it's the particles or the charged ions tend to stick or hug your magnetic field. And therefore, if you put this magnetic field, like for example in a donut shape, you could get your particles to spiral around in your donut shape. And there are other parts of this commonly known as the tokamak reactor, but I'm not going to go through that right now. We could go through it maybe afterwards. Okay, so if you create a magnetic field, charged particles will spiral around this. Now, this is sort of the most ideal for them. See, one of the main things is that right now the fusion reactors run at microseconds. They run for a very, very short amount of time. Now, when you want to produce electricity for mankind, you can't have lights turning on and off. And so what they'd like to do is to have constant fusion. And so what they try to do in these reactors, a particular type of reactor, which is most of the ones that are creating these hot plasmas right now, is try to keep it in some form of equilibrium. Try to keep the gas in some form of equilibrium. Now it turns out the plasma does not want to be in any type of equilibrium, and in fact wants to create points of high energy, of singularities, and wants to evolve. Now one of its evolution states is to create these concentrations. They sort of, instead of just spiraling around, it sort of starts to squeeze in and eventually pinch in on itself. and this is therefore called the pinch effect. Now what this is that you're looking at here is a lightning rod which has been hit by lightning and has been crunched like a tin can by simply magnetic and electrical effects. And then they actually did one for a tin can. Anyway. This is in the laboratory. They created this pinch effect, some magnetic influences, which crushed this can. Now this is very interesting because what they found is that if you, instead of trying to equalize the different effects that plasma naturally wants to do and allow it to evolve in some way and then use that evolution, you can get it to do many, many things. And so as far as the different ways you create fusion, the first one is you confine it magnetically, use a magnetic field to sort of keep the plasma around it and heat it up to the point where supposedly the atoms are now hitting each other really hard and are going to create fusion. The other way is this thing called a pinch, which is you let the plasma create this incredible high energy singularity and let that create the fusion. It won't be steady, it won't be constant, but you can just turn it back on. You can pulse it, is what they call. And that's one possibility. I don't think I actually have a picture of the next one. This is another way to deal with the fact that plasmas don't do what we think they're supposed to do, or maybe we're not doing what they think they're supposed to be doing. This is what's called a stellarator. And so what they found was that plasmas would start to twist. When you try to confine them, they start to twist and make themselves hard to combine. So instead of trying to deal with that, they try to make a reactor that twisted with the plasma. Okay, I don't know if this is actually how visible this is, but this is from, I think if you just look up, it's from Wikipedia, so you could search fusion reactors. And so I just went through the first two, for the whole magnetic fusion section, basically. Tokamaks, which are basically donut-shaped magnetic confinement reactors. Stellarators, which are sort of twisted versions of them. And then this other, I'm not going to go through all the other. All the other is actually very interesting. The one I will point out is this dense plasma focus, which actually is the subject of this plasma article that I mentioned before, Elementary Plasma Physics from an Advanced Standpoint. And its theme, its sort of theory, is to not only use one of the evolutions of the self-evolutions of the plasma, but to use several of them, several stages of evolution of the plasma to create fusion. And there's several videos that I can send out if people are interested about that. But that is being worked on right now at in New Jersey. Okay. Okay. And generally, okay. One more thing to point out. Okay, so on here, don't be fooled. Most of these actually don't exist. They are ones that have previously existed or are planned, are in some level of cutting, and so on. I'll give you a good example. So in the Americas, let's see, Alcotor C mod, as far as I can tell, has been cut, or is mostly cut. It is at MIT. The D3 is still functioning and is the best tokamak in the United States, and that's at General Atomic. UCLA, I don't think that one actually exists anymore. The one at the end here, TFTR, that definitely does not exist. And so on. So you just get a sense of this. I was going to circle these, but I didn't get time. Some of these do exist. In Asia, East is a China has two. China has East, and then another one called the PL2, I think. So they have two tokamaks. They also have a what's called an inertial confinement, which I'll go through in a second. Korea has a K-star. Japan has one, which I forgot the name of. Britain has the Jet, and then there's the Eater. So you don't have to know all of these, but just wanted to get a sense of the extent to which the research is. And it sounds like a lot, but it's really not. It's really not a lot. Like I said, most of the things on this list are not even, either are not functioning or being basically zeroed out in funding. Okay. So one more thing I'm going to go through is the bottom part of this chart. So inertial confinement. So there's the other form of fusion. Well, it's not the other form. One other form of fusion, one of the attempt at fusion, is basically to imitate the nuclear bomb. So the H-bomb, we know, worked. It definitely worked. They tried tests and sort of always works to some extent. But it's one of those things that if you throw a table at a nail, it will probably nail. But you don't really need a table. And what they try to do then is to say, okay, well, we know how to create a fusion reaction by throwing a nuclear bomb at it. Basically, is what they did, a fission bomb. For those who don't know, and I don't know exactly the design, I've seen several different drawings of the same thing, which are all slightly different. But the H bomb is a fusion fuel with a fission bomb basically attached to it in the same cavity. So you set off a fission reaction, which then compresses the fusion fuel and creates fusion. So they know that works. And so the going hypothesis is then, okay, well, what if we could put that same amount of energy, or less, preferably less, in, and create a controlled version of this bomb? And thus the National Ignition Facility in Livermore in California. So what they did was then set up a bunch of lasers, which most people I think have seen the animation. Is set up a bunch of lasers, which are surrounding this fusion fuel in a similar way to the way that the bomb would set up, the fission bomb would have affected the fusion fuel. Okay, and then I just want to go through, oops, one more thing. Let's see, how should I do this? I'm not sure if people can see this.
That's almost visible.
Almost visible? Okay, let me try to make it a little bit bigger. This is just a fun pedagogical, it's an infographic I found online. Just goes through temperatures. So just going up the temperature scale here. So here's the freezing point of water. 0 degrees Celsius, 32 degrees Fahrenheit. Ice cream melts at slightly less than that. And, okay, so there's water down here, melting of butter. Here's the human body temperature, 37 degrees Celsius, 98.6 degrees Fahrenheit. There's the boiling of water, 100 degrees Celsius and 212 degrees Fahrenheit. Here's the melting of lead at 326 degrees Celsius. The melting of aluminum. Oh, here's lava. Lava is at about 1,000 degrees Celsius. Melting of iron at 1,500. The boiling of lead at 1,750. Here's the surface of the sun. So the surface of the sun is supposedly 5,500 degrees Celsius. Here's the surface of a star, Sirius. Okay, the sun's core now. This is now it's getting really high, right? 13 million degrees. 13.6 million degrees Kelvin. So that's very close to Celsius. Now here's fusion. This is fusion on Earth. Fusion is happening, fusion is happening at 100 million degrees. Here's another reactor operating at 500 million degrees. Okay. So just to give you a sense of, yes, it's very, very hot, but usually heat has certain domains. So like almost everything that you deal with that's relative to life has, is between freezing and boiling of water. When you're dealing with these type of temperatures, 100 or 500 million degrees Kelvin or Celsius, you're dealing with a totally different domain. And there's something physically different than we're used to, which is allowing us to get into this type of these type of temperatures, these type of energies. Okay, so let's get to the economics here. I think most people have some form of idea of what having a lot of electricity is going to do for us. Yes, the more common things are, yes, we won't be coal reliant, we won't need petroleum for oil for energy, we'll be able to desalinate and use electrical everything and make fertilizers and change the weather and have real industry and so on. That's true, yes. With lots of energy, with lots of electricity, really, or energy, we will be able to do those things, which are actually things we know how to do now, but are not really being done at a sufficient level, or at all. Like, for example, using high heats for desalination and so on. And yes, that does have to be a point that is not diminished, but it has to be more than that. The way that Mr. LaRouche is dealing with fusion is really, I think, it's much more than just fusion energy, and it has to do with the way that he's now defining it as a driver. Actually, it's not even now. I guess he's been really defining it for decades now. Um, but and it gets down to what actually is a driver. Now, the last major driver we had was the Apollo program, and there were things that came out of it. If you look at these spin-off magazines from the Apollo program, you'll see a very good demonstration of the good economics and bad economics by looking at the year 73 and the year 83. And the difference, and that actually made clear what the difference is between a driver and a technology. So in 73, the spin-off reports talked about creating completely new sciences, so the entirely new science of stress analysis, of material science. And so being able to create, thus being able to create very long implements that don't break, that don't use any more material, but because they're shaped the right way, can go faster, and so on, therefore more productivity. In 83, still talking about the space program, but the spin-off reports are now reporting polarized sunglasses, greater feeling swimsuits, and Tang. And I think that the key to being able to understand the way that we're discussing fusion now as a science driver is going to be us being able to make that distinction between what actually changes the economy and what is just cool, what is just technology. And we recently ran into this, for example, with all the fracking technology, all the so-called jobs and so on around fracking. Now, we already went through how fusion has pushed a lot of these different, just the foundations of basic science, of physics, mechanics, of electromagnetics, and likely it's the reason they're pushing the limits of these different sciences is because there's a new science afoot. Like, for example, what occurred with Apollo, where there was completely new fields created. And from that is something that we're going to have to be able to imagine. We're going to be able to paint for ourselves a picture of a higher throughput economy. Now, let me just give you a couple examples. It would probably be the best. So I'm showing right now a picture of the power of lasers over several decades. Now the two lines are pulse lasers and constant lasers. So these are lasers which are constantly being run, or ones that are flashing, basically. And laser technology has increased tremendously. And if you look at over the years of SDI, for example, it was, it shot up almost vertically. If you look at the past 2 decades, though, you'll see that there is a flat line, and it's horizontal instead of vertical. Now, what's interesting, and this is, lasers are a good place to start as far as understanding what a physical or what a fusion economy will look like. Because, so for example, the way that a lot of these lasers are powerful or become powerful is not by putting more energy in. But I should have showed a video of the lasers. Anyway, but by actually taking the same amount of energy and compressing it down into a very small time span, and thereby creating densities of energy in a very small amount of space, so high energy flux density, which can do things that could not have been done before with even much, much more energy. One of these things is fusion. And I think Cody will probably go through some of this. Maybe Natalie can go through some of this later on today, too. She's sitting here with me. But with these higher energies, you don't just have more energy, like I was saying before. You know, if you have more electricity, then we can do more desalination, making more fertilizers. No, the key to a real driver is to be able to create a new state of not only the economy, as in having new technologies, but really you're dealing with a new mankind, a new way that we see each other, and a more developed way that we interact with the universe. And so, for example, with these lasers, I'll include some links to some videos, but with these lasers, we have been able to access nuclear properties and even some chemical ones, but at a much, much more precise level. So on their level. And therefore have been able to open up completely new a potential, that a domain that was previously just sort of a blur to us. Let me show you something. Let's see. So, whoops. I'm not sure if this can be seen.
Need to zoom in
Yeah, here we go.
a little bit more.
More? Okay, so even though this is not... Anyway, so this is one of the first examples that most fusion scientists point out when they think of things that came out of actual fusion research that has benefited mankind, and most people don't know it. So this is actually out of a report that I pulled up from 2001 from General Atomic, which goes through technologies that were built explicitly for fusion and that now are being used for other things. And I want to just point out a couple of them and how they relate, and how these relate to some basic principles of economics. So this one is not as clear, but I think it's a very fun one because people can relate to it. So, you know, we have these basically computers that are, you know, in our phones. We have these, what used to be incredibly fast computers in this small little device, and a bunch of other small little devices. Now, the reason that these can be so small is because of fusion. So the one is they use plasmas to create very thin films. That's from research in fusion. This other one is being able to, let's see, improve optics developed through laser fusion research. So improved optics developed through laser fusion research play a key role in producing and aligning the templates that control the deposition and etching of the microscopic channels and components of semiconductor wafers. So being able to create these tiny little invisible to us, invisible to our eyes, circuits. The development of intense UV or X-ray devices through fusion research can make semiconductors basically faster and smaller. And this is something that we could go into, or you could look it up as far as photolithography. So right now we create our semiconductor, our chips in here through light, and with that there's a basic limitation, which is the wavelength of light. You can't make your pieces smaller than the actual wavelength you're using for the light. Now, to make very, very high frequencies of light, so little tiny wavelengths, you need to go into the nuclear domain. That's just one example. Better examples, which I unfortunately didn't pull the pictures of for some reason, are laser machining, which are right now around. Laser machining using petawatt lasers. So these are, how many billions? 10 to the 15. What is that?
That's a quadrillion.
A quadrillion power for machining. Now, what does this do? So it's not just taking the same amount of heat. For example, if you're trying to heat up a piece of metal and just increasing that. No, what they've been able to do with the laser cutting is to be able to hit the metal so fast and at a frequency that's not resonant with the metal, so that it will cut but not warm anything. Now, the reason I bring that up is because when you're dealing with a driver, and this is a very good example, a very good. I think back at the Apollo days, the Apollo spin-offs I was discussing. There are certain effects that will propagate through the economy. So, one example is if you apply your 100 million degrees, or the precision which you're operating in the nuclear domain, or with these plasma singularities, if you apply that level of precision to the point of production, like at your machine tools, your raw material production, or so on, everything that goes down the line, including now the machines which you make with those machine tools, and and so on, we'll have that integrated in. We'll have that new principle, that new precision, integrated in to the economy. Now, if you have, now I'm not saying that things like laser microscalping, laser microsurgery, which is very cool, being able to zap little cells one at a time at different depths. I'm not saying that that's bad, but that's one technology. And what it should be is a reflection of a shift in the economy as a whole. And that's really, I'm working on a paper right now which will go through some of these technologies, and unfortunately I didn't really have time to pull up some of the pictures and different examples of this. But hopefully that would give you a little sense of what we're dealing with as a real science driver. So, one, yes, having the type of energy that could get us out of a water crisis. But two, really having the increased power over nature that is the type of power that Lynn discusses, that Mr. LaRouche discusses. It's this. Well, anyway. So power over nature, from that standpoint, and then being able to take that perspective and let that shape all of the current policies, the more so-called immediate policies. Anyway, I'm going to stop there for now and see if there's any questions. And then maybe go through some other things in the period. Oops.
What's that?
What's that?
What is that?
This?
Yeah.
Um,
Oh yeah, just
yeah.
Just playing with the plasma.
Yeah, he's playing with a flame. So he's trying to show that a flame actually is a plasma.
Can the people who are on speak?
I don't know.
Oh, you.
I think they can unmute themselves. Can you check the chat?
Yeah, Leona,
Yeah, who is this?
Rachel.
Hi, Rachel.
Hi. That chart you had that was a curve going from hydrogen to helium and went down, curved back up, and it was something about the change in mass, but unequivalent change in energy or something.
Right.
What was that exactly? I didn't. Yeah, get why it's a continuous curve and exactly what happened.
Okay, yeah. This actually, this is a way to account for something that is anomalous. And what is anomalous about it what is anomalous is that atoms are not equal, first of all, and they're not additive. So, for example, so for example, lithium-6 is not exactly half the mass of carbon-12. So then, this is a fraction of, well, anyway, the fraction doesn't really matter, but the scale is appropriate. So the way that they try to account for this is you take all of the nucleons, the things in the nucleus, and you divide it by its mass, by the total mass, and you get this. But the main thing is that, so because there's this disparity, so what it seems like is that a proton in hydrogen weighs more than a proton in carbon. That's basically what it comes down to. Whether it does or not, that's not what's being claimed here. I think this is just a way to explain this anomaly, but because that is the phenomenon, we've been able to take that disparity, that difference in mass, and hypothesize what reactions we have to create to take that mass and turn it into energy. And so in this case, any conversion from hydrogen to something higher, tritium or helium or lithium or helium, will introduce a release of energy. Does that make sense?
Yeah, for the most part. You said a proton of hydrogen would not equal a proton of basically anything else, or what did you say?
Yeah, right. So they do not seem to be the same particle, though supposedly they are.
Okay, yeah.
Leona,
Yeah.
it's Bill. Hi.
Hi.
Why is it that to get the increase of power in lasers that you were describing that as a function of nuclear processes? Could you get into that a bit more?
Yeah. The increased power, the reason that they produce lasers now at such high powers, such that it can basically, you can't shoot it through air because it reacts, it splits, it cracks air. You know, it cracks hydrogen into its pieces. They produced the lasers originally for NIF, for the National Ignition Facility. So that's where that came from. Now those lasers have also been used to create minuscule amounts of fusion, so one atom at a time or two atoms at a time. And all they do is actually it's, I think Natalie can explain it more. She stepped out of the room, but they've been able to, one, shoot a laser, create a wake, so basically like a shock wave. And oh no, actually this is, you should just explain this part. How do they create fusion with a petawatt laser?
Oh. So they create neutrons. What they do is the laser is so powerful and so fast that they can ionize the gas really quickly. And then before so you have the energy impact, and then the nuclei and the electrons split apart really fast. And before the electrons realize what has happened, they hit it again and then get the nuclei to fuse together. So it's really a matter of the intensity and the time frame in which it's happening. I don't know what the question was though.
Yeah.
Yeah. So you can't, I mean, you're not going to be able to create excess energy or net energy with that, at least right now, but they're at least creating fusion neutrons.
You also get a sense of what domain you're dealing with to be able to shock an atom and act upon it before it realizes what's happening.
Hey, Leona?
Yeah.
It's Juliet. Can you say a little bit about how chemistry is going to be revolutionized? Or what are some of the cracks that we see now, besides just maybe the mass example is one of them? I don't know. Are there other examples?
Yeah, no, I can think of two right now. One is the ability to catalyze chemical reactions, basically, through radiation that comes from basically nuclear processes, so UV, X-rays, and things like that. So basically being able to tune to a particular chemical reaction, chemical bond, and be able to act upon that level. There's that. You may get lost in this. Maybe I should put a video. I should write down things I can put a video about. There's a short animation of cold fusion. which is pretty fun. Cold fusion is sometimes called chemically assisted fusion, or the more common one is low energy nuclear reactions. But the chemically assisted fusion is actually is right on. And so what you're dealing with what you're dealing with in that is you're actually using the properties, seemingly chemical or at least structural properties of another something else, a solid. In most cases, it's palladium or a mix of palladium and nickel, and using the structural properties to create the confinement or the resonance that's required for fusion. At least that's one model. Either way, whether the model is true or not, what that has posed is that there's something anomalous which is creating this effect, which seems to be fusion, which we don't understand from a chemical or structural standpoint about matter. And I think more work on that, for example, would definitely put into question some of our supposed thorough understanding of how crystals and material structures and chemical bonds work. Those are just two examples. Do you have anything else?
Hey Liona, this is Jared.
Hi.
Right. So when you're saying that we have fusion now, but then we're also saying that we have to develop fusion, but it seems confusing to me that sometimes people are saying we can do fusion now and then we have to develop it further and have it in 10 years or something, like this ITER reactor report. And I'm just wanting more clarification on that. What can we do now, and what are we supposed to do in 10 years?
Yeah. Okay, so we did fusion. We did fusion with the nuclear bomb. So we've had fusion for at least that long, and we've hypothesized fusion much, much longer than that. The question is, at what level? And so, yes, a lot of these reactors that I described and other ones that have been zeroed out create fusion. The only thing that it's kind of a funny selling point is that the one thing that is supposed to be the goal right now for fusion is what's called break even. So the ability to create energy out of your fusion reaction that's more than what you put in for everything. So that's the magnets, the electricity, heating up the plasma, and everything. Ideally, you would want the energy that comes out of the fusion reactions that you make. So not just a couple, but enough you want that energy to be more than all that which you put in. And some of that is going to depend on letting that fusion reaction occur at a level which is heating the plasma on its own from that energy. So they call that ignition. And once that's occurring, then it's sort of self-feeding and also producing excess energy. So that's one side of it. That's what they're saying is 10, 15, 20 years away. Like ITER's first burning plasma, yeah, is supposed to be in, I think, 2025 now. They pushed it back another 5 years. So that's not fusion energy on the grid. That's just one of the steps into fusion. Now, there's all sorts of skepticism around it, and we can go into that, but there are other ones that are actually just heading towards electricity production, basically. Now, like I said, that's sort of a narrow view. I think it's a narrow view. Yes, we do want fusion energy, but that doesn't mean that everything that we've done so far that hasn't led to fusion energy has been just a dump into a black hole. Things like this have already occurred. You know, these are the little, you know, mammals in the dinosaur period. But we've already seen the effects of fusion funding on the economy, although we may not designate it as that. And so that's where it gets really sort of tricky, but also more exciting, because there are other things you can do with fusion that are going to be incredible. Like, for example, fusion can create, with the type of fusion they're working on now, lots of neutrons, which are great at transforming other atoms into other things. And so people are talking about taking all that so-called nuclear waste, the used fuel, and transmuting that into something useful and other medical isotopes. And there's fusion propulsion, which is not really concerned with break-even energy. And it's much, much less concerned with cost. And so on, and some of the things we discussed, but it's that's what they're talking about. It's sort of an accounting thing, I think. They're talking about energy, you know, which really puts it on the same level as the natural gas. That's why they can argue that, right? Natural gas, solar energy, and fusion energy as sort of an alternative energy. But really, that's not what we're dealing with. We're not dealing with just another energy source. That will be sort of an effect. Just like, you know, with NWAPA, the water system itself will be an effect of our increase in understanding, production, training, and so on, of the whole weather system and our population. And yeah, I don't know if that answers your question, but
Just maybe, just I mean, you basically said it, but when people are talking about getting fusion, we're really talking about generating electricity, creating net energy in mass, in a, you know, a large quantity of energy. What we can do right now is we can do fusion. We can fuse nuclei of atoms together. We can do that, and but it's done in a very small scale. So we can generate neutrons, and the reason that when you hear about these kids, like, oh, 13-year-old kid makes fusion reactor, they're able to generate neutrons on a very small level. So they're showing the effect of fusing these nuclei together and getting these neutrons, which proves that fusion has occurred. And we have different applications for this. So you need a neutron source to, for example, transmutate elements for medical isotopes. You have to create radioactive elements to be able to do nuclear imaging, which is extremely useful for cancer treatments, for medical imaging, and there's different uses to just create these neutrons. So we can do fusion on that level, but in terms of actually generating energy, that's the real breakthrough that's going to be fundamental for revolutionizing the economy.
okay. we done?
Any questions from the live studio audience?
Well, I guess the thing that really did strike me from the Bardwell article, right, is the and the paragraph in particular that you read from is this question of plasma as being a self-developing, evolutionary, involved in evolutionary processes, unlike other substances that we're aware of, right? So, because it seems to me that that study of plasma physics as such is very much connected to this larger concept of the fusion economy.
Mm-hmm.
So I'd be curious about how that, specifically taking it from that angle, the evolutionary processes of plasma, it can be thought of in terms of the coming fusion economy.
Okay, so could people hear that or no? I want to take that as a no. So Daniel asked, from this article, the elementary plasma physics from an advanced standpoint, the article discusses this concept of the evolution of plasmas in the process of fusion, basically, and the what the larger role of understanding that is for the economy, yes, or for mankind, basically. And I think, there's two things that I think really need to be developed, and I'd have to do a lot more work on this, but one is, yes, because we're dealing with something now that breaks with all of the mechanics, all of the Newtonian mechanics. We do have a potential now to one, to challenge all of that so-called science, the foundations of modern day science, from the standpoint of, for example, Harkins, Moon, Ampere, these guys who really were looking at this arc and also just nuclear power or nuclear processes very, very differently. And Lynn's been discussing this idea of the two triads. I don't know if he calls them that now. I guess we've called them that now. The small and the large with Cusa and Brunelleschi and Kepler, but then also Planck and Einstein, and then Vernadsky not really resolving the small and the large are posed by Planck and Einstein. And I think this actually poses the study of what plasma really is, gets closer at this idea that Lynn is discussing, because one, you are dealing with this paradox of the small and the large. You are dealing with something that seems to be driving a larger process, as well as something very small. But then, two, the fact that plasmas act in a way that seem to be sort of like an organism that evolves, that acts as a whole, and has all these other transformative properties, does seem like it takes a Keplerian way of thinking in order to approach the problem afresh. So we need a Kepler type of science in order to deal with what, technically, this goes back at the question that that Jared asked. If we have fusion, then why don't we have fusion? What is Lynn talking about that is the fusion driver? Well, there are a lot of things that we could do before we understood and could control them.
Mhm.
And that made all the difference in the world. You know, we used nanotechnology when we created churches in the BCs, or I mean not the BCs, but at least in these really old churches. But we didn't understand them as nanotechnology. Now we do. That makes a big difference. We control it. And so the other thing that I think is going to be really interesting is being able to bring back this discussion, which Bernowski did bring in, of life and cognitive processes as basic science, as a basic property of the universe. Because you know, as we've seen with several other things, when you get to these types of extremes, like when you deal with superconductivity, or you're dealing with quantum processes, or you're dealing with very, very hotter than star plasmas, you start to run into these extremes where we have properties where you run into properties that you only really face with in life when you're dealing with biological or noetic processes. And you see again where in the extreme, the abiotic starts to reflect a process which is higher than itself, which is maybe subsuming itself. And so I think we will start to, it's the right way to approach it. This gives us a window into the right way to approach it, and into bringing these studies of life back into physics.
I just wanted to add something
Yeah.
to Daniel's question, which also ties into what Jared said. But I think to the extent that we are able to advance our knowledge of universal principles, we're going to advance economic science if we're thinking about economic science in the right way. And plasma, first of all, is the most abundant state of matter in the universe. And to be able to make a breakthrough in fusion, I think we're going to have to go out into space. We're going to have to expand the space program, and we're going to have to really investigate how the stars work, which is how fusion works. All of these anomalies that we're seeing in plasma physics are only anomalies in a reductionist framework, in the limited view that we have right now, because we're stuck in science. For example, the sun, the solar wind is a plasma. The solar wind, when it leaves the surface of the Earth, so it's not even, it's about 10 million degrees Fahrenheit, leaving the surface of the Earth, the surface of the sun, as it leaves, it accelerates to about 3 times its speed, and it heats up. So this is completely strange to us in terms of standard physics. It would be the way that it's described. It would be as though you were boiling water on your stove, and instead of the steam just dispersing and then disappearing and cooling down, it suddenly started to heat up and concentrate its energy and make some type of heat spear of of steam. And that's what the solar wind does. That's a completely normal, common process in the universe. And we are stuck because we're in this very temperate zone on Earth, and we're calling these other plasma processes anomalies, when really what we experience are anomalies in terms of the way the universe acts. So the more that we can explore these common processes of the universe, the more that we're going to understand universal principles, and the more that we're going to advance economic science, say just generally. And that's also the case against entropy as a state of the universe.
What that makes me think is that maybe if we get an understanding of that, we'll get an understanding of whether there's an evolution inside of atoms that's expressed in things like decay and things like that. Which nowadays is very little understood.
Did you want to come and elaborate? I can't summarize what you're saying. Or you can just say so they can hear you.
Yeah.
If you.
I was just thinking from what was mentioned that if we gain an understanding of the evolution of plasmas, perhaps we would also gain an understanding of the evolution inside of atoms, like for example radioactive materials which decay after a certain time, and how fast they decay depends on how much how much of a material you have. It's obviously interacting with itself, but that seems to be like another expression of something like evolution, even though it's less developed. But, yeah.
I have a question from Israel, or from Mexico. No?
Houston.
Houston. From Houston. What role does Dr. Moon's research play into fusion? And I can only partially answer that from whatever I know. And what I've heard, at least, is that one, Moon looked at, he looked at nuclear processes very differently than most people, or than the common explanation is now. One of the big things is that the nuclear reactions, like for example, nuclear decay is considered a sort of random process, and they say that you don't know exactly which atom is going to decay in an ore, but all you can know is that half of it will be gone in what's called the half-life time. So you can know in the general process that there's going to be a transformation, but you don't know which one and when. And Moon didn't like that. Moon didn't like the idea of that there's something statistical and anything random about physical processes. And he saw chemical or nuclear transformations as some type of, his hypothesis was that it was some type of reflection of physical space-time in the large operating. And to some extent you see that in Schnoll's work. But his idea was really, when you're looking at nuclear processes, you're not just looking at something in the small, but that you're always investigating, he was always investigating the shape of space. And I know we've published most on his work on the Moon model and the atomic nucleus, but he really did a lot before that. And his idea is really, there is no, he actually has something very controversial, which Chuck has said, and I'd have to confirm this, but he says all fusion is cold fusion. And basically his idea is you're dealing with tuning. There's no process of just smashing things together. And if you smash things together at even a high enough speed, like you say, but you don't understand the tuning process, it still won't work. It also works the other way around, which is you may be able to create fusion with much, much less energy were you to understand what's actually going on. And some of this is the spin polarization example is very good, which is, you know, Lynn had this hypothesis in the 80s, or in the early 80s, that if you could spin polarize fuel, if you could make the deuterium and tritium at the same or opposite spins, it sort of depends on which reaction you're dealing with, but a particular spin that you control, then you can make nuclear reactions occur at much less energies, at much less lower energies, and mainly because you're dealing with a some aspect of the nuclear process that you previously really hadn't considered. And so I think that's the main thing that Moon contributes, and of course the other thing is that Moon is part of this arc of development, which I can only mention because I really haven't been able to do a whole lot of work into. But it is what the Fusion Energy Foundation was based on. Yeah, I don't know. I mean, that definitely is not a view that is being taken today. People do not say that they're investigating the shape of space when you're looking at a nuclear transformation or anything like that.
And just in terms of the looking at the shape of space, we have a couple of approaches in fusion today. One of them, which is the tokamak version, the tokamak approach, is that you're working to try to tame the plasma. And the main problem that they're coming up against is the plasma wants to misbehave. It wants to increase its energy and make these concentrations of energy, these waves. And what they have a couple of approaches to dealing with this. One of them is that you can provoke the plasma so that it acts up just a little bit, and you have little ripples on the edge of the plasma that you can then control. And they do this by various ways. There's magnetic coils. There are an approach where you shoot a frozen hydrogen pellet into it. And this is based on the assumption that, well, the plasma is always going to want to act crazy, so let's just make it act slightly crazy and then deal with that smaller scale craziness. Okay, so then there's a completely different approach, which is working with that known tendency of the plasma and creating a design that coheres with that natural geometry of the plasma and uses it to your advantage. And I would say that would be more along the lines of the way that Dr. Moon would look at it, at least in the sense that, because he was essentially saying that you can eliminate the Coulomb barrier, this very strong force that exists once you get to nuclei very close together. There's a very strong force of repulsion that you can somehow eliminate this barrier or that barrier that doesn't really exist. That there was some evidence that in the hydrogen bomb that the Coulomb barrier did not exist. So if you take the approach of looking at the geometry of the plasma and working with that, that is, I'd say, yeah, just a completely different approach than trying to fight the current.
Okay.
And we just had another question about books to read on plasma, and Leona had mentioned before that we were going to put together a reading list, so that will be done.
I think we should post it on the description or separate. We'll post it somewhere.
We'll get it out.
Put a short one up first, and then have a fuller one later. Need some
we got
video
another
too.
question here.
Okay.
This is just something on the moon model. In the initial reports on cold fusion, the experiment was using palladium as the electrode, and palladium in the moon model has depleted platonic shells from the tetrahedron, icosahedron, dodecahedron, and the initial hypothesis was that the palladium was able to absorb a huge amount of hydrogen in its structure,
Right.
and that was providing force-free pathways for the fusion. So that's something that was hypothesized, but then the cold fusion itself was attacked viciously, and
Yeah.
I don't think any other experiments have been done on it.
As far as I know, we actually talked to somebody who's performing those experiments now, and you might know him, George Miley. So as far as I know, though, that the research hasn't progressed an incredible amount since then, but it is still being worked on at a very small level. That's great. There's actually I think it's a Nova special, which is just called nuclear fusion energy. And I thought it was going to be about nuclear fusion, but it was actually a whole special on the cover-up of cold fusion.
Is that recent?
I actually couldn't, it was posted on YouTube in 2013. I could put a link to it, but I don't know when it was made. It has some cinematography. It has some video editing things that are funny. But I think as a history, and one, it has a history, but two, it makes it really explicit that it was a political attack on. It was a political attack, and it was a severe reaction from the scientific community to basically having all the fundamentals of science challenged. Okay, the list. Videos. Okay, good. Anything else?
Great, thanks.
Okay, good. I hope that was helpful. Good night.
Next.